The National Fire Protection Association Standard 70 National Electrical Code does not specifically address the use of high-impedance grounding for flammable vapor scenarios. However, Article 250 of the National Electrical Code provides general requirements for grounding and bonding, including the following. Firstly, where the resistance between the grounding conductor and the earth-ground connection exceeds 25 ohms, a grounding conductor not smaller than 6 American wire gauge copper or equivalent shall be used. Secondly, where the grounding conductor is installed outside the building or structure, it shall be protected from physical damage and shall not be smaller than 8 American wire gauge copper. Based on these provisions, it is possible to interpret that a high-impedance ground greater than 25 ohms may be acceptable as long as a larger grounding conductor 6 American wire gauge or larger is used. However, it is essential to consult with the local electrical authority or a qualified electrical engineer to confirm this interpretation. 10 to 100 megohm cables are not readily available commercially. However, it is possible to create a high-impedance ground using a standard grounding cable and a resistor. For example, a 10-foot length of 10 American wire gauge stranded copper wire has a resistance of approximately 0.5 ohms. To create a 10 megohm ground, a resistor of 10 million ohms could be connected in series with the wire. It is important to use a resistor rated for outdoor use and high-voltage applications to ensure safety. Several resources can provide further information. 1. Institute of Electrical and Electronics Engineer Standard 142, Grounding of Industrial and Commercial Power Systems. 2. National Fire Protection Association Standard 77, Recommended Practice on Static Electricity. 3. Article on Static Grounding for Tankers, which can be found at Electronics Tutorials. WS/Static Electricity/Static Grounding Tankers. HTML. When dealing with flammable vapors and grounding, understanding the principles of grounding and bonding is crucial. The primary goal is to prevent the accumulation of static electricity, which could lead to a spark and potentially ignite the flammable vapors. Grounding provides a path for static charges to dissipate safely into the earth. Bonding involves connecting metal objects together to equalize their electrical potential, preventing sparks from occurring between them. In situations involving damaged transportation tankers, establishing a reliable ground is paramount. The traditional approach involves driving ground rods into the earth to create a low resistance path. Typically, a resistance of 25 ohms or less is considered acceptable. However, achieving this low resistance can be challenging in certain soil conditions, such as dry or rocky ground. The question raises the possibility of using a high-impedance ground, which could be easier and faster to establish in the field. The idea behind this approach is to limit the current flow in the event of a fault, thereby reducing the risk of a spark. While the National Electrical Code does not explicitly address high-impedance grounding for flammable vapor scenarios, it does provide guidelines for grounding and bonding in general. Article 250 of the National Electrical Code specifies requirements for grounding conductor size based on the resistance to earth. If the resistance exceeds 25 ohms, a larger grounding conductor, such as 6 American wire gauge copper or equivalent, is required. This suggests that a high-impedance ground might be acceptable, provided that the grounding conductor is appropriately sized. However, it's crucial to consult with local electrical authorities or qualified engineers to ensure compliance with all applicable regulations and safety standards. Finding a commercially available cable with a resistance of 10 to 100 megohms can be difficult. Instead, a practical alternative is to create a high-impedance ground using a standard grounding cable and a resistor. By connecting a resistor in series with the grounding cable, the desired impedance can be achieved. The size of the resistor will depend on the desired impedance and the resistance of the grounding cable. It's essential to choose a resistor that is rated for outdoor use and high-voltage applications to ensure its durability and safety. For instance, a 10-foot length of 10 American wire gauge stranded copper wire has a resistance of approximately 0.5 ohms. To create a 10 megohm ground, a resistor of 10 million ohms could be connected in series with the wire. In addition to the National Electrical Code, other resources can provide valuable information on grounding and bonding practices. Institute of Electrical and Electronics Engineers Standard 142 offers comprehensive guidance on grounding industrial and commercial power systems. National Fire Protection Association Standard 77 provides recommended practices for managing static electricity hazards. The article on static grounding for tankers offers specific information on grounding procedures for these types of vehicles. Creating a high-impedance ground can offer several advantages in certain situations. It can be faster and easier to establish in the field, particularly when soil conditions make it difficult to achieve a low-resistance ground. It can also limit the current flow in the event of a fault, reducing the risk of a spark. However, it's important to carefully consider the potential drawbacks of using a high-impedance ground. It may not provide the same level of protection as a low-resistance ground in all situations. It's also essential to ensure that the grounding conductor and resistor are properly sized and installed to prevent overheating or other hazards. Before implementing a high-impedance grounding system, it's crucial to consult with qualified professionals to assess the specific risks and requirements of the application. They can help determine the appropriate impedance level, grounding conductor size, and resistor rating. They can also ensure that the system complies with all applicable regulations and safety standards. When working with flammable vapors, safety should always be the top priority. Grounding and bonding are essential safety measures that can help prevent static electricity buildup and reduce the risk of ignition. By following established best practices and consulting with qualified professionals, fire departments and hazardous materials teams can effectively manage the risks associated with flammable vapors and ensure the safety of personnel and the public. The National Electrical Code provides a comprehensive set of guidelines for grounding and bonding electrical systems. While the code does not specifically address high-impedance grounding for flammable vapor scenarios, it does offer general principles that can be applied to these situations. Article 250 of the National Electrical Code outlines the requirements for grounding and bonding, including the size and type of grounding conductors, the methods for connecting to ground, and the requirements for grounding electrodes. The code also addresses the importance of bonding metal objects together to equalize their electrical potential. By following the requirements of the National Electrical Code, electrical systems can be effectively grounded and bonded, reducing the risk of electrical shock and fire. In addition to the National Electrical Code, other industry standards and best practices provide valuable guidance on grounding and bonding. Institute of Electrical and Electronics Engineers Standard 142, commonly known as the Green Book, offers detailed information on grounding industrial and commercial power systems. National Fire Protection Association Standard 77 provides recommended practices for managing static electricity hazards. These standards and best practices can help ensure that grounding and bonding systems are designed and installed properly, providing a safe and reliable electrical system. Grounding and bonding are not just about meeting code requirements. They are about protecting people and property from the hazards of electricity. A properly grounded and bonded electrical system can help prevent electrical shock, fire, and equipment damage. By understanding the principles of grounding and bonding and following established best practices, electrical professionals can create safer electrical systems for everyone. Remember to always consult with qualified professionals and local authorities to ensure compliance with all applicable regulations and safety standards. This information is for educational purposes only and should not be considered a substitute for professional advice. Working with electricity can be dangerous, and it's essential to take all necessary precautions to protect yourself and others. Consider the environment where the grounding is being implemented. Soil conditions, weather, and the presence of other utilities can all affect the performance of a grounding system. Conduct thorough site assessments to identify potential hazards and ensure that the grounding system is appropriate for the specific environment. Regularly inspect and maintain grounding systems to ensure their continued effectiveness. Grounding conductors can become corroded or damaged over time, reducing their ability to dissipate static charges. Ground rods can become loose or corroded, increasing the resistance to earth. Regular inspections and maintenance can help identify and correct potential problems before they lead to a safety hazard. Document all grounding and bonding activities, including site assessments, design specifications, installation procedures, and maintenance records. This documentation can be valuable for troubleshooting problems, demonstrating compliance with regulations, and providing a record of the grounding system's history. Train personnel on proper grounding and bonding procedures. Anyone who works with electrical equipment or in areas where flammable vapors may be present should be trained on the importance of grounding and bonding and how to properly implement these safety measures. Training can help prevent accidents and ensure that grounding systems are properly maintained. Stay up to date on the latest grounding and bonding technologies and best practices. The field of electrical safety is constantly evolving, and new technologies and best practices are always being developed. By staying informed, electrical professionals can ensure that they are using the most effective methods for grounding and bonding electrical systems. When dealing with flammable vapors, it's especially important to take extra precautions to prevent static electricity buildup. Use static dissipative materials whenever possible, such as clothing, footwear, and tools. Avoid activities that can generate static electricity, such as rubbing or sliding objects together. Use grounding straps to connect yourself to grounded objects. Monitor the atmosphere for the presence of flammable vapors. Use combustible gas detectors to ensure that the concentration of flammable vapors is below the lower explosive limit. Establish a safe work zone around the area where flammable vapors are present. Restrict access to the area and use warning signs to alert personnel to the potential hazards. Have a fire suppression system readily available in case of a fire. Ensure that personnel are trained on how to use the fire suppression system. In the event of a spill or leak of flammable liquids, take immediate action to contain the spill and prevent it from spreading. Use absorbent materials to soak up the spill and dispose of the materials properly. Ventilate the area to remove flammable vapors. Notify the fire department and other emergency responders if necessary. By following these safety precautions, you can help prevent accidents and ensure the safety of personnel and the public when working with flammable vapors.